Today we're going to be taking a look at cool GCD and LCM techniques like these ones over here and how they trivialize complex problems like this, in addition to learning about the Euclidean algorithm and many other cool examples. But if you haven't checked out the previous video, be sure to check that out. It's on divisibility, Legendre's theorem, and has some very cool problems like this one. Let's get started. So GCD LCM, GCD is just the greatest common divisor, LCM is the least common multiple. And for GCD, you just look at all of the lower exponents from each of the prime factors to find the GCD. And the LCM, you look at the maximum exponent of each of the numbers to find the LCM. And a cool fact is that GCD of the two numbers times LCM of two numbers is just a product. That's a pretty cool identity. So we have another interesting identity over here. So this identity states that the GCD of numbers AC and BC is just C times the GCD of A and B. And this intuitively makes sense because C is anyways a common factor between both AC and BC. So it will be a factor of the GCD as well. So this is a very powerful identity. We're going to be using it quite often in this video. Okay. Let's take a look at this example that seems hard, but we'll see how to solve it. Two numbers A and B satisfy the condition. The LCM of the GCD of 24 and A and the GCD of A and B is the LCM of the GCD of 24 and B and then GCD A and B. And we're asked to find if A is 2B, what is the smallest possible value of A plus B? So how do we do this? This is very complicated. We've got LCMs of GCDs. I mean, how do we even deal with something like this? Well, here's how I'm going to visualize. I would say would be the easiest way to visualize something like that. So the easiest way to visualize something like this is to, well, draw a Venn diagram. So let's draw three circles. Oops. I'm going to draw three circles, and what each of those three circles will represent are the prime factors of A, B, or 24. So what does that mean? Well, I'll explain in a second, but essentially all the possible prime factors of that number will be part of that Venn diagram section if that is the case. So for example, let's say this is A, B, and 24. Basically, the key thing here is that all of the prime factors of A will be in this circle here. So and the factors that are common to both A and B will be in this region here. The factors that are common to both A and B. And similarly, the factors that are common to both, the prime factors, of course, that are common to both A and 24 will be in there. So let's just try to understand how this is going to work. Let's say A is 36. And let's say it shares a factor of 2 and 3 with B. Then 2 and 3 goes here, and the other 2 and 3 go in the A region, in the only A region. So now there's a 2 and 3 that are common to both A and B, and that would represent the GCD of A and B, right? Because that's the prime factors in between. And then A would be this region here, the only A region. Okay, so now that we understand how this model is going to work, how do we encode our problem with this Venn diagram thing here? Okay, first of all, GCD 24 and A. What is GCD 24 and A? Okay, so the thing about GCD 24 and A is that GCD of 24A is just going to be the region that's common to both the 24 and A circles. So that's this region right here. That's GCD 24A. What about GCD AB? Well, that's going to be this region over here. Maybe let me do it this way. This region over here will be GCD AB. All the primes inside this region here will be GCD AB. And the LCM of these two regions, well, notice how this region is counted in both the GCD of 24A and AB. So the LCM will just be this whole region together, because it represents all the prime factors that are in either of the GCD terms that are underlined with orange and blue. So this whole region right here, let's just call it the blue region, whatever, these represent all the prime factors in this term here. Now, what about the second condition? Well, it turns out that the second condition is actually quite symmetric. Well, so the reason it's symmetric is because, well, notice how in the problem that it says that over here that we have GCD 24b and AB. But for A, it was GCD 24a and AB. So the only thing different is that instead of GCD 24a, it's GCD 24b. So let's just mark this with red. It's the GCD 24b, which is this region here, and GCD AB, which is this region here. And that represents the LCM. This whole red region represents the LCM of both terms, where the prime factors are again inside one of these bubbles. Okay, so what does that mean if they're equal? Well, notice how this region is common to both the blue and the red regions. It's blue and it's red. It's part of both regions essentially. Or sorry, not that region. This region over here, all of this black area is common to both the blue and the red regions. And well, what does that mean? That means that all of the prime factors in this remaining blue region must be the same as the prime factors in this remaining red region, because these quantities are equal. So if all of those prime factors remaining must be the same, well, what else does that mean? Well, notice how this part on the center is common to both regions anyway, both this region and this region here. Because that center region is common to both regions anyway, we can also just say that the prime factors in here, in this area over here, is the same as the prime factors in this area over here, which essentially means that what we're saying is the GCD, for this condition to be true, for our condition to be satisfied, we must have GCD 24a equal GCD 24b. So essentially what we just did with this Venn diagram thing over here is we simplified this giant complicated mess of a thing here and made it into something like this. GCD 24a equals GCD of 24 and b by our Venn diagram here. Okay, so now what's next? How do we find the answer from here? Well, notice how in the problem it states that A equals 2b. A equals 2b. So, well, this means that GCD 24 2b equals GCD 24 and b. So just because the greatest common factor is the common factors that belong to both b and 24 in this case, and by giving b an additional factor of 2, the GCD is unchanged, which means that this additional factor of 2 is not also shared by the 24. So this additional factor of 2, let's say 24 also had an additional factor of 2, then the GCD would be 2 times greater. But the thing is, it doesn't, because these GCDs are the same. So what this essentially means is that B and 2B, those must both have, B must have 3 powers of 2, at least 3 powers of 2. So it has to be a multiple of 2 cubed. Now the reason this is true is because in this case, let's say it was GCD of 24 and 16, where B is equal to 8, B is 2 cubed, and equals GCD of 24 and 8. Notice how this is a GCD of 8, and this also has a GCD of 8, because this extra power of 2, this extra factor of 2, doesn't increase the GCD, because all the other powers of 2, 8, are already part of 24, are already taken by 24. So by giving 8 one more factor of 2, it's not increasing the GCD, because 24 only has 3 factors of 2 available. So it can, with GCD of something with 3 factors of 2 and 4 factors of 2 is just 3 factors of 2, which is 8. But what if it was something else, like GCD? What if B was just 4, not 2 cubed? Then is this true? GCD of 24/8 equals GCD 24 and 24/4. Well, this GCD is 4 and this is 8, so clearly not. Now again, this is true because in this case, 24 has factors of 2, and 4 only has 2. So by giving 4 another factor of 2, now both of them have, now the GCD will also have another factor of 2. Versus in this case, it already had maxed out. They both already had 3. So increasing 1 won't increase the GCD, because GCD is the minimum from both exponents, like I mentioned earlier. So therefore, what this essentially states is that b has to be a multiple of 2 cubed. And the smallest possible multiple of 2 cubed is none other than 8, of course, because, yeah, it has to be 8. So, because it must be 8, then that means b must be equal to 8. And if b is equal to 8, then a, which is 2b, is 16. So their sum is 24, and that is the answer for this one here. Okay, now we're going to move on to the Euclidean algorithm. Sounds fancy, but basically all that it states is that GCD of x and y, well, you can add any number of multiples of y to x, and the GCD will remain the same. You can add, you can subtract, you can whatever. And it's very useful because let's say you're trying to find some big GCD like 186 and 92. What you can do is you can say that one from 186, we can subtract two multiples of 92. So 186 minus 2 times 92, which is 184, and then comma 92. These GCDs are equal because all we did was we subtracted multiples of 92. And then from here we get GCD of 2, 92. And now from here, what we can do is we can subtract multiples of 2 from 92. If we subtract multiples of 2 from 92, we can subtract any number we'd like. So we would get GCD of 2 and 92 minus 92, because we can subtract any multiple of 2. So that's GCD of 2, 0, which is 2. The GCD of any number in 0 is just that number, because 0 is basically divisible by everything, because anything times 0 is 0. So essentially we can use this for breaking down this large GCD, taking the larger term, subtracting multiples of the smaller term, and making it simpler expressions like this. Okay, now we've got a cool example from the AIME. So in this problem over here, we've got a sequence where an is 100 plus n squared. 100 plus n squared. And we're asked to find, for each n, the greatest common divisor of an and an plus 1. Find the maximum value of dn over all values of n through the positive integers. Well, first of all, what is d of n? In terms of n, of course. Let's write this out, just to make it clear. D of n equals GCD an, comma, an plus 1 in our notation. And let's plug in these values based on the sequence. GCD 100 plus n squared, comma, an plus 1 is 100 plus n plus 1 squared. Cool. And then, now what we do is we're ready for the Euclidean algorithm part. How do we evaluate this? Like, first of all, how do we find the maximum value of this? The trick is Euclidean algorithm. And why do we use the Euclidean algorithm? Because we noticed that these terms, they have a lot of common terms. I mean, if you let's expand out. If you expand out n plus 1 squared, you get n squared plus 2n plus 1. And these terms are almost identical except for that 2n plus 1 there, right? So what we're going to do is, by Euclidean algorithm, we subtract the smaller number, any multiple of the smaller number, it could be 1, from the larger number. So GCD of 100 plus n squared, so the smaller number, and you take this number minus any number of multiples of this to get what the other term will be in our GCD. So what we can say is that this is 100 plus n squared plus 2n plus 1 minus 100 plus n squared. So that leaves 2n plus 1. So that means that this expression here, by the Euclidean algorithm, is just GCD 100 plus n squared, comma, 2n plus 1, as you can see over there. So, well, what do we do with this? I mean, do we apply Euclidean algorithm again, and what do we do? Well, the tricky part here is that To apply the Euclidean algorithm again, we would have to subtract n by 2 multiples of 2n plus 1. Because in order to get the n squared term to cancel, that's our goal, right? To make it from something plus n squared to just n's, and then maybe even to constants. Who knows what we'll end up with. So there's actually two ways to proceed from here. One is you could do casework, and this is the hard way, which I'm not going to show. You could do casework based on whether n was even or odd, and then subtract multiples accordingly, because n by 2 won't always be an integer. And that would work, but it's a little messy and it takes a while. So instead, here's another even cooler solution. So the trick here is noticing that 2n plus 1 is odd. So the GCD of something, when something is odd, well, we can multiply as many powers of 2 to 100 plus n squared as we'd like. It won't change the GCD. Why won't it change the GCD? Well, GCD of, let's say, 2 to the a times 100 plus n squared, something like that. It wouldn't change the GCD because having 2 to the a in one term does not make any of these 2 to the powers as part of the common factors of both terms over there. So here's a clever trick you can actually do. You can actually multiply this whole thing by 4. Yes, 4. Now why 4? Because now it's very easy to just subtract multiples of 2n plus 1 very easily. So the trick here would be to now subtract 2n multiples of 2n plus 1. So that would be GCD 4n squared plus 400 minus 2n times this quantity over here. And what is that quantity over there equal to? 2n times 2n plus 1. Right? That's 4n squared plus 2n. And that's it. Or not it yet, but that's it for our GCD expression over there. If that's by Euclidean algorithm, of course, because we're subtracting 2n multiples of that. 2n plus 1, finishing the Euclidean algorithm step. And now we just do some simplification. 4n squares cancel. We're left with 400 minus 2n, comma, n plus 2n plus 1. Now, I know we've been doing a lot of subtraction here with Euclidean algorithm, but you don't always have to do subtraction. As you can see here, we're actually going to do a little bit of addition with the Euclidean algorithm. So what does that mean? Well, that means that what we're going to say is that this is equal to GCD 400 minus 2n plus 2n plus 1, comma 2n plus 1. Now you might be wondering, why am I doing this, making it even bigger? Well, it's actually because these 2n terms will now cancel out. And we're left with GCD 401 and 2n plus 1. And we want to find the maximum value of this as it ranges through n. But what is the maximum value of GCD of 401 with something? Well, it turns out it's actually just going to be 401. Why? Well, because if n is 200, then 401, then it's just GCD 401 and 401, and that works. But there's no other higher value possible than 401, because how can we achieve a value larger than 401 when 401 is one of our terms in GCD? GCD will make two numbers smaller. It's their greatest common factor. It's taking the common parts common to both. So no matter what number this is, you'll never exceed 401. We'll never exceed 401 because this can never have any factors that are not 401 and that be part of the GCD. So our answer is simply 401, and that is the cool solution. So let's summarize. What we did is we see what that expression is, we simplified it, and then we see this cool trick of multiplying by 4. And then we do that, we add 2n plus 1 to cancel out the 2n. We always trying to get rid of any terms. So generally with Euclidean algorithm, you always want to get rid of these excess terms like 2n, n squared. Just always try to make it simpler. Don't try to make it more complicated. Like if you have GCD of 3n plus 2n plus 1, you don't want to make it a square term on your left side. You're trying to simplify things. So subtract to cancel out n's, add whenever needed to cancel out n's as well. And maybe just like we did, we want to cancel out these n squared terms. So that's kind of the key idea here. And now you can find all these practice problems, free book AMC 1012 preparation, link in the description. First link, you can click on it, download completely for free. But now we're next to move on to modular arithmetic. And this is kind of the heart and soul of number theory. They fund the core, and it's super useful for solving problems that seem tricky like this one, and even more complicated problems like this one and many more. And they'll be looking at how to solve many more tricky problems in the next class. You can find that video clicking right there. You click on it right here.